rather quickly. So the idea here is that it's giving you a vector, I think they call it v, right? And you have a force vector, right? And what they're asking you, so let's just talk about this. So you have your force vector. And what is this right here? What is this green one? And then what is this? Matt, can you turn off the light just so you can see the colors?
The projection of F onto the vector
V, yeah. So it's the component of F in the V direction, right? The component of F. And what did we call this right here? We called the green one what? V parallel. F parallel, sorry, yeah. So we have F parallel, and I just don't really like it because there's too many dang letters. And F perp, which just doesn't sound right. So what can you tell me about the relationship between those three colored vectors? What do you know? F parallel plus F, and you said the colors, I like that. F perp is equal to F, right? So you know that, correct? We also learned yesterday that what's the magnitude of F parallel equal to? We learned this yesterday. What is that equal to? Hold on. This is hard enough even with one person speaking, okay? So just, Tori, go. The dot product of what?
F times the unit vector of V.
The magnitude here is this dot what?
The unit vector of V.
What do you think, everybody? Is it the unit vector or is it V itself? It is the unit vector or V itself. Because does it matter? Hold on. I understand. I haven't finished writing it right now. I understand what you're saying. So they usually call it like U. They just say U is equal to the unit vector in the direction V, correct? Okay. So if we write this out just with what we have right now, you could say it's V. So you could do this, all divided by what? Because this is too big, right? The magnitude of V. Very good. Because what is this right here? Can someone just tell me what this is right here? That is the unit. That is the unit vector in the what? In the V direction, right?
The dot and you basically divide both sides by.
You divide it. You this right here, this top thing right here. Dot product gives you what? Does that give you a scalar or a vector?
Scalar.
Gives you a scalar, right? So you just find it and then you divide at the end. I mean, the thing is, yes, you could put that magnitude in at the beginning and then do the dot product, but does it matter? Not numerically, but what would you rather do? Make the fraction at the beginning and have to carry all those fractions through, or just do it at the end? Just do it at the end. So if we do this one out, let's just actually do this one out. What for 19? What does it tell you V is? I think it's the same thing. 3i plus 4j, like this.
Wait, I thought we're missing something. We need to multiply.
Yeah, I did F times U, or the F dot U.
Okay.
That
Divided by 5, because it's a 3, 4, 5. The magnitude is 5. Because you know that the magnitude of V is 5. So what do we have for this V unit? 3 over 5 I plus 4 over 5 j. How are we doing so far, Ray? We're doing okay so far? Okay, so we could, if we wanted to, divide by 5 at the end, or we can divide now. That's fine, whichever one you want. So now what are we going to dot together to find this magnitude? F, and it gives you F, right? That's what changes every time, right? For 19, it's 0.2I plus, minus what? And we have there 0.5J, right? So if we want to actually find the magnitude of F parallel, what do we need to do? We're doing the dot of two vectors here. We have them. Yeah, we have F dot V unit, and do we now actually have the components of each of those? Yeah, we have, and I'm going to write this in the bracket form. You have 3/5 comma 4/5, and what's the other one?
0.2 negative.
Yeah, 0.2 comma negative 0.5. So if you do this out, could someone just give me the two? What does it come out to be? Does anybody have it?
Turns out into 0.28.
Is it 0.28?
Yeah.
Do you agree with that, Ray? Is that it? Okay, hold on a second, kids. This right here is the magnitude of F parallel, right?
Yeah.
But now, to get a vector, we need a magnitude and a direction, right? What's our direction?
V.
The unit. We want this. This is our direction, right? So what do we want if we actually want F parallel? Not the magnitude of it, but we want F parallel like this. What's it going to be? How do we find it? Hold on. Remember, once again, kids, it's hard enough to hear just one. Let's use hands again. Tori, go. What is it?
It's negative 0.168I minus 0.22 over J.
Negative, what is it?
0.168I
Yep.
minus 0.276.
So it should be plus.
Or 224.
Yeah, the 2.
Here, this is A. Great. What does B ask you for?
Wait.
Okay. Yeah, we had a Mars rover. We had a Mars satellite crash. You heard about that like 6 or 7 years ago?
Yeah.
150 million, like hundreds of millions of dollars was lost because one team was working in meters and another team was working in feet. Awesome! Like, just like any word problem, we're looking, let's say, U and V add together to get what? A. Is that correct?
Yep.
You know, let's just say that U is parallel to D.
Yeah.
And V is perpendicular to D. So what does that mean if they're perpendicular? What do you know? You know that V dot D is equal to none. To 0. Ling, right? Ling is 0, right? And what do you know about parallel?
There's a ratio.
Yeah, so you know that U is equal to some. They like using lambda as their scalar multiple is this. Correct?
Yeah.
So do you see this, everybody? So at this point, all you've done right now is simplify what they've told you. That's all you've done. You could now try to generate equations that you could solve simultaneously to get U and D. Does that make sense, everybody? So for example, so we could write these out. We could say V is equal to V1I plus V2J. Why is it good to have common notation when we do this? You know which one we're talking about? Yes, I understand that I picked V and U, and why is that a poor choice in a way?
Similar.
They look so similar. The only reason I'm sticking with it is that's just how many of these problems are going to be presented with you in the book, and you got to get used to it.
It's just so funny they choose the most
Yes!
easy one.
M and N, P and Q. Yesterday I had a meltdown. Like, I had to write P and Q like 100 times, and I like lost the P, Q, and Y in the same question in Algebra 2, and I like lost the ability to write. Like, I just couldn't do it. I would try. My hand would try to write like Y, P, and Q all at the same time, and it would come out like this. I'm like, oh, that's something, but it's not what we want. Okay.
Even DNA.
DNA. It's like, great, DNA. And if you're really good today, I will show you some cool math posters. And I'm not even putting the bars over the vectors, okay? So just deal with me. Okay, so are we okay so far?
Why is D indifferent?
D is
We know D.
Oh, I'm sorry. We know D already. Excuse me. Don't create more work than you need. Okay. Okay, so which do you want to plot? Who got this far? One or two of you? A different way, but are you okay with me so far?
Yeah.
So let's go with this. Let's see how long it goes. I might pause if we get slogged down in some algebra. Let's try it out for us. Okay, what's V equal to here? So we know. So what does this tell us? This side on the right tells us that VI times 2, right? Plus, sorry, V1. V1. I'll put it in front. So we know that 2V1 minus what? Minus 4V2 plus what? V3 is equal to what? Does everybody understand how I got that right there?
Yeah.
Yes.
But are you okay with it so far? Are we okay with that? Yeah, and then you could do the other side, right? You could do it the other way. We're going to leave it as 1. Okay, so what do we now know about U here? We know that U is going to be equal to what? U is going to be equal to lambda, and what's D? Lambda 2I minus lambda 4j plus lambda k. Okay. And we know that they add together to get what?
A.
And we know that they add together to get A. So we have something here.
U and V. And
The dot product, which dot product?
No,
So
U
U dot W has to equal what?
W dot V.
W dot V. Absolutely.
I think they're not equal with respect to their magnitude.
They're equal with respect to their magnitude.
Because the magnitude of V and W is not the same.
True. Okay, so that's true. So how do we correct for that?
You just put the magnitude on the other side.
The magnitude. Okay, hold on. We need to understand moving forward. First, dot product is a scalar value. It's one value. A cross product is a vector. And the third thing you have to understand before we move forward is the thing you really, really have to focus on, and you should have been, but really going forward, you need to make sure you have an idea of an understanding of the big picture, not necessarily the minutia of the proofs. Because I will show you in a second that some of the proofs are terrible. And not because you won't understand them, but because it's just a ton of algebra that you never have to do more than once. When the book just tells you something and says no mention of why, that's a warning sign that if you go look it up, you might be blinded. Okay, just be careful. I also went back and looked up and clipped into your notes the answer book solutions to the two questions we were working on. The first one is, we're totally on the right track here, agreeing with the book. This is the one we just did. It's great. It works out. You can read about some of the logic. Our method for this one totally will work. It will work if you grind it out a whole lot. There's a more straightforward way, which is actually using the parallel and perpendicular vector relationships that we have. You can do this one. It wants you to have two things that add together that are perpendicular to each other to get a third. Oh, that's a vector projection. You can use the relationships that we have for vector projections to make the algebra simpler. So I put that in there. You can take a look. But this is what we need to look at right now, which is cross products, cross products, cross products. So just remember, the big picture right here is what you need to focus on, and have some faith that the algebra is there. You need the height off of this right angle right here, right? And what's the area of a rectangle? Base times height. So then you can translate the area of a parallelogram. You can chop it into two triangles, move the triangle over, and you get the area of a parallelogram. So if you were to write this area, this parallelogram, how would you write the area of this parallelogram? You'd write it as the magnitude of vector v times the times, so that's the base, and what's the height of this thing? Yeah, W, magnitude of, times sine of theta. So if you have two vectors in a plane, there you go. You can find the angle. If you know the angle between, can you find the angle between?
Sure, why not?
You could. Do you have a way to find the angle between two? You have law of cosines. You have lots of different ways to do it. It gets a little nasty if you use the algebraic method. The thing though is, are we always going to be dealing with two dimensions? No. Notice here. We define the cross product of the vectors v and w, written v cross w. Hey, look at notation with a cross. Yay, another way to have something you've seen before mean something completely different.
I'm over this.
Okay,
Come
well,
up with new symbols.
okay. To be a vector perpendicular to both v and w. So if you have two vectors in 3 space and you want a vector perpendicular to both of them, you will take the cross product. You will take the cross product. Think back to a question I asked you a couple days ago. Here are 3 points in a plane. And I asked you to find the equation for that plane. Well, you agreed with me that that's a unique plane because 3 points, not in a line, define a unique plane. But what do you need to define a plane to write the equation? You need a point. Well, I gave you 3 of them. But you also needed the normal vector, right? And you guys played around with it for a while and it was like, it's hard because you can get vectors in that plane, but then finding something that dots to be 0 is hard, right? We now have, or you will have shortly, a quick way to get perpendicular vectors. Because you can get perpendicular vectors, you can do lots of cool things. Find distance between things. Write the equations of planes. These are very important. But you'll respite from the storm of new stuff, okay? Some respite. This is just an extension of, they just said, here's some stuff. This is the definition of cross product. Cross product is a scalar or a vector. It's a vector. The magnitude of that vector is
Scalar and the area
a scalar, and the area of the parallelogram formed by the two base vectors, right? It also told you that it goes in the direction that is perpendicular to both, right? Perpendicular to both. So what does this say? V cross W is the area of the parallelogram with edges, if they actually write it out, times this, right? Because this is a vector. What is n defined as? The normal. The normal right there, okay? So what this says is, this right here, remember this, the magnitude of the two vectors sine theta? What did we say the magnitude of the two vectors is times sine theta? That was just a way to write the what? The area of the parallelogram, right? So this is the area of the parallelogram, and this is n, the normal vector, but it's the normal unit vector. What's the magnitude of a unit vector?
No.
1. So what's the definition of this right here? This thing right here is a vector, right? It's going in the direction that is perpendicular to both v and w. But what's the magnitude of it? The area right here, okay? Okay. You have to have some things on faith right now. That's all it's saying. This is just restating that paragraph, which they just said accepted as true, okay? Because I think the typesetter was like, I cannot type that out. Here, it makes it look even worse. Not just because it's really hard to see, but this says the algebraic definition of cross product, v cross w, is this thing times I, so a scalar times I, plus a scalar times j, plus a scalar times k. So this is still a vector, right? And this looks horrible. Do you agree with me?
Yeah, sure.
Does this look horrible?
Yeah.
Yes.
The nice thing about this is there's a really easy way to remember this, what looks like regurgitated vowels and consonants. There's an easy way to remember it. And that's the big thing I want you to walk away with today, okay? And some of you have seen determinants before, some of you have not, so this is going to be varying level of clarity / difficulty / understanding. I understand 2x2 matrix. This is just a sidebar because we have to understand what a 2x2 determinant is before we do a 3x3 determinant. If you have a matrix A, B, C, D, has anybody seen something like that before?
Yeah.
Okay. A, B, C, D, that's a 2x2 matrix. You can only take determinants of square matrices. You might have done things, have you ever inverted a matrix before?
Yeah.
Maybe, kind of, sort of.
This is like
Real long time ago. But here's the deal. This is what you need to remember. Mechanically, the determinant of a 2x2 matrix is going to be AD minus, anybody remember?
BC.
BC. So the way you remember that, it's the cross product. But it's always what? Minus. Minus. Do you see the minus there? Minus. Is that important? Just go like this. Yes, it's important. The minus is hugely important, okay? So again, you can only take determinants of square matrices. You can only take determinants of square matrices. Is everybody with me so far? So the real question then becomes, let's say you had A, B, C, D, E, F, G, H, I. And remember, these have nothing to do with the vectors yet. I'm just arbitrarily choosing things in order, okay? Has anybody done a 3x3 determinant before? Okay, so the way you do a 3x3 determinant, and it might have been explained to you a little differently. There's several ways to think about it. You can break a 3x3 determinant into 2x2 determinants. The rule extends upward. Is there such thing as a determinant of a 4x4 matrix? Yes. You can break a 4x4 matrix down into 4 3x3 determinants. And you can break each 3x3 determinant down into 3 2x2 determinants, right? This is something that computers are very good at because it is very, very mechanical. Am I ever going to have you compute a 4x4 determinant by hand? No. But 3x3 determinant? Yeah. It's something that you can do. It's not impossible. You just have to be careful. So this is how you do it. The first thing you do is you look at this one right here. You look at that one right there, and that just gets to be parked right there. Is this ringing any bells? That's going to be the coefficient. Which 2x2 determinant do I now do? Does anybody remember which 2x2 determinant? Ray, which one do I do? Yeah. So what you do is you take A, and the next thing you do is you just cross all these out, and what's left? EF, HI. What is the 2x2 determinant of those four? EI minus HF. Does it? Yeah. The order is important. Not for products, it's not going to change it, but you might say it differently. Okay, so after you do A, which one do you think is next? B is next, right here. What did I tell you to do once you circle the B? Cross. I'm sorry, that just went away. It should blink back. Like this?
Yeah.
What's left now? So what's it going to be? B times what? DI minus FG. And I left something out there, which we're going to come back to in a second. I did not glue them together yet, because you can help me with this. Then you do the exact same thing for what? C, and you end up with C times what? EG. Now, can anybody tell me what operations you have to have here and here? Does anybody remember? There's actually, I'll start at the beginning just so you can remember it as a pattern. I did not put a sign here, here, or here. Does anybody remember what they are?
Plus, minus.
Plus, minus, plus. plus, minus, plus. Say it with me. Plus, minus, plus. You're going to remember everything else, and then everything's going to fall apart because you don't remember that one minus sign, okay? So it goes plus, minus, plus. If you do a 4x4 determinant, it goes plus, minus, minus. So here's the thing. This is something you learn because when you can use matrices to do many different things. You can use matrices to do codes. You can use matrices to invert things. I know we only have like 2 seconds left. But the idea is this right here correlates exactly to this. But it correlates to this, everybody. Do not pack up. Do not pass go. Here's what it correlates to. You ready for the punchline of our first foray into this? I, J, K, V1, V2, V3, U1, U2, U3. If you do the determinant written out like that, do you know what you end up with? You end up with the cross product.
What percent is cross?
Now the question is, there's nuances to this. Remember, I want you to focus on the big ideas. Because here's the thing. Is there going to be a structural difference between V cross U and U cross V? Yes, there is. One of them, remember how I told you the perpendicular vector can go this way or it can go that way? If you cross one way, it'll go up, and if you cross the other way, it'll go down. So what that means is this or this. Can you switch the rows? Yeah, you can switch U and V. It doesn't change, but it'll change the direction. But anyway, this is, again, the first time through this, I am just giving you the big ideas. We will fill in the minutia, okay? This is the cross product vector. Yay! Very nice. I'm really glad.